Andrews and Bruce Burnt. So what I'd like to say is the legacy of Ramanujan Conference, and now we are doing the legacy of Srinivas Kotyada and Kalyan Chakrabarti Conference for their 60th birthdays. The only difference is that instead of 1 hour, I have to give this talk in 30 minutes. So naturally, I won't be going through all the slides of this talk. So this is joint work with my PhD student Jason Johnson, who just on December 4th defended his thesis successfully. So he just completed his PhD. So this is sort of a rough outline of the talk. I will focus on 1 and 2, talk a little bit about the analytic approach, and then without going into too many details, I will discuss the main ideas relating to the uniform distribution of the second largest prime factor and how that gives the main result. Okay, so let us begin with the 2 classical results of Edmund Landau, who showed that the sum of the Mobius function up to x, which is denoted by m of x, is little o of x, and the series summation mu of n over n from 1 to infinity being 0, both of these are elementarily equivalent to the prime number theorem. That means if you assume these results, without too much difficulty, you can deduce the prime number theorem, and vice versa. If you assume the prime number theorem in its simplest form, pi of x asymptotic to x over log x, you can get both of these results. Okay, so this is famous 2 equivalent theorems of Edmund Landau. All right. Now, of course, strong form of the prime number theorem with error terms yield corresponding bounds for m of x and corresponding bounds for the tail n from x to infinity of summation mu of n over n. Okay, so they are very similar. All right. Now, this work actually goes back to my PhD thesis of 1977. Just to make one comment, after the Ramanujan centennial, the focus of my research shifted to the theory of partitions and Q-series, hypergeometric series. So for 25 years, I was not working in analytic number theory. I came back because 2 or 3 PhD students came and said that they would like to do the PhD with me and want to work in analytic number theory. But also there's something else that happened. These results in my PhD thesis of 1977, which was, I won't use the word ignored, but which was not so seriously looked at by the international mathematical community, suddenly got the focus from about 2017 onwards, primarily due to the efforts of Ken Ono, and now there are a whole bunch of papers relating to this, which they have termed as Aladi duality. So that was another motivation for me to go back and look at this work and see other problems that can be given to these PhD students. So I'll come to that very soon. So the very interesting duality that I noticed in 1977, actually when I was here in Madras for the summer, that's when I found this, was you take any function f defined on the primes. Little p of d is the smallest prime factor of d, capital P of d is the largest prime factor of d. So if I sum mu d, f of the smallest prime factor of d, over all divisors of n which are bigger than or equal to 2, I end up getting minus f of the largest prime factor of n, and vice versa. So I was quite excited noticing this because it is so simple and it is elegant, so I knew that it has to have some consequences, right? So I started investigating consequences of this. So here is one very interesting result. If f is a bounded function on the primes such that this function has an average over the largest prime factor, let's say the average is c, then the series from 2 to infinity, mu of n, f of the smallest prime factor of n divided by n, is minus c, and vice versa. So if the series converges, then that average exists, but it's c to minus c. Okay, so this is the result that you get as a consequence of that duality. Of course, quite a bit of analytic work is needed to get this, but this is the result that you get. Okay. Now, this is actually a surprising generalization of Landau's result. So take Landau's series, summation mu of n over n from 1 to infinity equal to 0. Remove the first term. So write it as summation mu of n from 2 to infinity is minus 1. Now go back to this equivalence. Choose your function f on the primes to be identically 1. Then obviously the average is 1, so C is 1. And that means the sum in 6, mu of n over n from 2 to infinity is minus 1. So that's Landau's result. So my result here is a very broad generalization of Landau's theorem. Okay, so I was quite excited when I got this. But we need some striking special cases. To make any theory interesting, you must have some really striking special cases. So the special case is the following. Choose your function f on the primes to be the characteristic function of primes in an arithmetic progression L mod k. So now the point is this. The prime number theorem for arithmetic progressions says that the sequence of primes is uniformly distributed in the reduced residue classes modulo k. So one of the things I proved was, if you assume the prime number theorem for arithmetic progressions, then from that you can show that the sequence of largest prime factors, that means it is the sequence of primes but with repetition, right? Like largest prime factor of 2 is 2, largest prime factor of 3 is 3, largest prime factor of 4 is 2. So it is really a sequence of primes but with repetition. That repetition does not destroy the uniform distribution property. It takes some effort to prove this. So I proved that the sequence of largest prime factors is uniformly distributed in the reduced residue classes modulo k, which means if f is chosen to be the characteristic function of the sequence of primes in the reduced residue class, this average C is 1 over phi of k, which means the series mu of n over n from 2 to infinity, but now with the condition smallest prime factor is L mod k, will be equal to minus 1 over phi of k. Now this is very surprising. Why? Because what is really happening is that series is convergent, conditionally convergent, and it goes to minus 1, and you are slicing that convergent series into phi of k sub-series. But you are slicing it in such a way that all the sub-series have the same value, minus 1 over phi of k. I don't know of any other example of slicing convergent series into equal valued sub-series. Divergent is easy. You take harmonic series that diverges, take the sub-series of all reciprocals of evens, reciprocals of odds, because in a divergent series like that, the contribution comes at the end, so it's the asymptotic distribution that is important. In a convergent series, it's very sensitive to the initial values, so you can't just slice it and say, I will now get 5 sub-series all equal to 1/5 of the original value. I have challenge. It's not easy. So this is the first example I found of slicing such a series. So I was quite excited by this. But what is interesting is, this is related to the prime number theorem for arithmetic progressions, just as Landau's result is related to the prime number theorem. So this was my PhD thesis. And what happened was, from 2017 onwards, this has received considerable attention and generalized in the setting of algebraic number theory by the use of the Shebatarov density theorem. I'll come to that later in the lecture, by a whole group of young mathematicians, but primarily with the impetus given by Ken Ono. So these references will come later. Okay. So now, in that same 1977 paper, I had higher order dualities. So here pk of n, capital Pk of n and little pk of n represent the largest and smallest prime factors of a number. Of course, these are defined only when the number has at least k prime factors. So you set f to be equal to 0 if omega n is less than k, the number of distinct prime factors k. But now the duality is, if I sum mu d, f of the kth largest prime factor of d, okay, I do not get the smallest, kth smallest, I get actually only the smallest, but with weight omega n minus 1, choose k minus 1 with a sign attached. And then this can be reversed. Okay, so this is the higher order duality. All right. And if you use Mobius inversion, you can rewrite those two identities in this particular form. Now, I never investigated consequences of this higher order duality say after 1977, and nobody did, which doesn't mean it's uninteresting. It's just that people didn't look at it. And sometimes when people don't look at something, it's an opportunity for you to do something interesting. So after Ken Ono and this group started looking at these algebraic analogs, another PhD student came along, Jason Johnson, and I said, you know what, we should look at these higher order dualities and let's look at k equal to 2 to begin with, and let's see what we end up getting. So that's the thrust of this talk. So when you have k equal to 0, k equal to 2, that's the identity that I'm looking at with the smallest prime factor. Now, just as you have summation mu of n over n from 1 to infinity is 0, you can show that summation mu of n omega n over n from 1 to infinity is 0, but this is more difficult to prove, okay? And I will tell you what is involved in the proof of this. But now if I peel off the first term corresponding to n equal to 1, like I did for the classical Landau result, I still end up getting, so the sum from 2 to infinity, mu n omega n over n is still 0. Previously I had a minus 1, but now it's still 0. Okay, so the main result now is, just as we proved there that the sequence of largest prime factors is uniformly distributed modulo k, we now prove that the sequence of second largest prime factors is uniformly distributed modulo k. But this proof is more difficult compared to the distribution of the largest prime factor, and I will tell you why it's more difficult. But once you have that and we use our duality, you can show, and this is our main result, that if I take that series mu n omega n over n from 2 to infinity, but now I impose the condition smallest prime factor is L mod k, I once again get 0 for every residue class L, which means I have taken that original series whose value is 0 and sliced it into phi of k equal valued subseries, and of course all equal values are equal to 0. Okay, so this comes out as a consequence. So this is our result, and recently we have posted this paper on the archive. So I'm going to give you some idea as to how we get this. Okay, so now I want to tell you a fundamental difference between the largest prime factor and the second largest prime factor. The fundamental difference is this really important counting function, psi of xy. This is there's a typo there. It's largest prime factor less than y. So this is the number of integers up to x whose largest prime factor is less than or equal to y. This is actually quite small when y gets small compared to x. So let's denote by alpha the ratio of logarithms of x and y, which means y is x to the power 1 over alpha. So as alpha increases, so square root of x, cube root of x, fourth root of x, and so on, the psi of xy becomes much smaller in comparison with x, and it's x times, this is an actual bound, e to the minus alpha over 2, but it's even much smaller than this. Whereas, if you look at the second largest prime factor and ask for the number of integers up to x for which the second largest prime factor is less than or equal to y, it is not that small. Why is it not that small? If you choose the second largest prime factor equal to 2, you can't make it smaller than that. Every number of the form 2 times the prime has second largest prime factor 2. And so the number of such integers is of the order of magnitude x over log x. Of course it's little o of x, but it's not that small in comparison with x. So naturally when y gets bigger, it's maybe still little o of x, but it's not going to be as small as psi of xy. So that makes all the computations much more difficult, because many of these convergent things have to be handled much more carefully because of the fundamental difference between the growth rate of psi of xy and psi 2xy. So I just mentioned this as a fact. Okay. All right. So next difference. The sign m of x, which is the upper bound is given here. This comes from the strong form of the prime number theorem. It changes sign infinitely often. In the case of summation mu n omega n, that should be an n by the way, this sum m omega of x is asymptotic to constant x over log squared x, which means it will not change sign infinitely often. But it does change sign for another reason, but only finitely many times. Okay, so it's on the same side. All right. So there is a significant difference between the behavior, and that actually adds to the complication of this, of establishing these results in this particular case. All right, so I just want to say exactly how we do this very quickly. So what we do is we look at m omega of x, which is this sum that I have. I express this omega n as the sum over the count of the number of prime divisors of n, and I reverse the order of summation. So I get a summation mu of n over integers which are 0 mod p. You write n as m times p. Because of the Mobius function, your m and p must be relatively prime. So I rewritten this way, so it leads to the investigation of a sum which I call mp of x over p, and that is the sum of the Mobius function up to x, where these numbers n will not have a prime factor p, and one can obtain a uniform bound using the Perron integral method that's valid for all p up to x. Okay, so this comes out. All right. And once we get that, we have to go back and split this sum into two ranges, p less than or equal to t and p bigger than t, and work with this, choose t optimally, and when you do that, you end up getting a bound which is only of the size of x over log x. And this x over log x is because the primes come in, and without further investigation of the cancellation, you can't do any better. So you get a bound of x over log x, but that's still good enough. It's still little o of x. Now the next thing you do is a very familiar technique to all the analytic number theorists here. You take the same sum and put a fractional part of x over n as a weight. You go through the method of Axer, and then you end up getting little o of x, but there is a loss in terms of the quality of the upper bound. The final thing is you look at the integral part. Now you use the fact that if you sum mu d omega d, that is the negative of the characteristic function of the prime powers. So when you do that, this sum becomes minus x over log x, and you add everything up, you end up getting the fact that this sum becomes 0 because I have to divide by x, and that is how you first get the sum mu of n omega n over n, and from 1 to infinity and 2 to infinity to be equal to 0. Okay, good. Now, I just want to make one comment about analytic approach to such sums very quickly. So we go back to this idea of Selberg, who in 1950s looked at what he called as the generalized divisor function, which are the coefficients, Dirichlet coefficients in the expansion of zeta s to the power of z, but z is a complex number. And using the Perron integral method, he showed that this is x log x to the z minus 1 over gamma z. But the only difference is that since z is a complex number, the zeta s to the z has a branch point. So you can't just go around, it's not a pole, so you've got to do a lasset. And when you do a lasset, it turns out that you get the Hankel contour for the gamma function, and that's how you end up with a gamma z at the bottom. So this is Selberg's result, and it's uniform in any bounded circle, absolute z less than or equal to r. Now, Selberg noticed that you can deal not just with zeta s to the power of z, you can multiply it with some other Dirichlet series, which is convergent or analytic in real part s greater than half, and he gave some important examples of this to solve a certain question of Hardy on the local distribution of the number of prime factors. Okay. Now, the case of interest for us here is summation mu of n z to the omega of m. Now, why is this of interest? Because when I differentiate this with respect to z, the omega n comes down, and then I get z to the omega n minus 1. So then if I put z equal to 1, that's my sum mu of n omega n. So it can be obtained from the Selberg thing by differentiation with respect to z. So what you do is you write down the Dirichlet generating function, which is this, and you rewrite it in terms of the Riemann zeta function to the power minus z, and then you get this function, which is analytic in real part s bigger than half. And so the Selberg method yields this estimate here. Now what I'm going to do is the following. I can heuristically take the derivative of this with respect to z and put z equal to 1. That's what your summation mu and omega n is. So waving the hands, ignoring the error term, if I just do the main term and take the derivative, I end up getting x over log squared x. But that's only a heuristic. You still have to justify that, because you can't just take derivative like that when there is an error term. So we, Delange extended the Selberg's method by saying, instead of just having zeta s to the power z, you can multiply it with log zeta s to a positive integral power, a negative integral power. The branch point thing is still the same, so the Selberg method will go through. So now this is called the Selberg-Delange method, and this is a natural extension of Selberg's method, and Tenenbaum has a thorough account in his book about this. So when you do that, you actually end up getting, this is what you get heuristically, but you can establish this rigorously by the Selberg-Delange method. Okay, so now these are the details of the heuristic derivation by taking formal derivatives. But now what is happening is, and this Tenenbaum wrote in a letter to me after I pointed out these results, he says that you can actually get a series expansion like you get for the logarithmic integral of x. Here you can get a series expansion in terms of log squared, log cubed, etc., with an error term that is comparable to the prime number theorem. So he said you can prove the results that I have in a stronger form if you use the analytic approach. But the point I want to make is, when I use duality and go on to primes and arithmetic progressions, these analytic techniques, we don't know how to apply, and even Tenenbaum didn't know how to apply. So the elementary methods that I had used previously with access theorem and so on, that still works. So one must have a great respect for elementary methods because they are of wide applicability, wider applicability sometimes than analytic methods, because analytic methods demand that your generating functions must have specific properties, because otherwise you cannot apply the analytic methods. Okay. All right. So moving on. All right. So as I said, the fundamental counting function for us is this well-known function psi of xy. So here I have it correctly, largest prime factor less than or equal to y. For a uniform bound, one can use something like this. But if one needs sharper bounds, you can use the Dickmann function, which is given by an integral differential equation or a difference differential equation. And this function actually decays quite rapidly, much more rapidly than the reciprocal of the gamma function. Okay. Now, a simple but a point to be immediately resolved. The largest prime factor is uniquely defined. But there are two definitions for the second largest prime factor. You can either say, I take an integer n, I remove the largest prime factor, and I ask what is the largest one remaining. If the largest prime factor repeats, then it is the same prime factor remaining. Or you can say it is the second largest prime factor defined to be strictly less than the largest prime factor. So one of the first results we have to prove is that there is little difference in these two methods of defining the second largest prime factor. So that's what this theorem says. This theorem says that the number of positive integers up to x for which the largest prime factor repeats is this small. So you don't have to worry about which of the two definitions you use. In this paper, we use the definition that the second largest prime factor is strictly less than the largest prime factor. Okay. So I'm not getting, this is the proof here using the psi xy, but I'm skipping it. Okay. The next thing I need to prove is that the second largest prime factor is almost always large. So what do I mean by that? By that I mean the number of integers up to x for which the second largest prime factor is not that big, so in this case I put an e to the root log x, is actually quite small. And here is a stronger version of that result. Okay. The reason I need this is we're going to use the prime number theorem and the prime number theorem for arithmetic progressions. So we're going to replace sums over primes with Stieltjes integrals, but when we do that, unless the p is large, it makes no sense. You don't use the prime number theorem for p less than 100. You only use it p going to infinity. So that's why I need a result of this type. Okay. So anyway, we've got this bound. It's technically difficult to prove. I've got some calculations here, but again I will skip this. But an elementary proof can be given of that. Now this result is the one that sets up everything. So this says that the number of integers up to x for which the second largest prime factor is congruent to L mod k is x over phi of k plus an error term of this type. Now in my 1977 paper, when I proved the same result for the largest prime factor, this error term was x over e to the log x to the 1/3. I used the de la Vallée-Poussin error of e to the square root log x, but when I apply that, I pay a price because of the repetition. And that repetition gives me e to the log x to the 1/3. Okay, so there is a price to be paid. All right, so it doesn't matter. It's still much bigger than any high power of log x. So here I'm not able to get an error term of that precision, but this is what we're able to prove. Now, how do I prove this? I'm going to just explain a trick, and after that I will conclude by telling you about recent work. The trick is the following. You look at all the integers up to x and classify those integers according to the second largest prime factor. But when you do that, you have to ignore the primes because they don't have a second largest prime factor. So there is a built-in error of x over log x in your calculation due to you have to discard the primes. So that's what I have here. Okay. So the identity is your S2 of xp is the number of integers up to x with a fixed second largest prime factor equal to p. And when you do that, when I sum over all p less than or equal to square root of x, I get all the integers up to x minus the integers which have one prime factor, and those are the x over log x plus this. Now the next thing we do is, I want to understand this. So I take the same sum, break it up, but I want to focus on the largest prime factor, so I write it in a certain form. But the main point is, I express it in terms of this Dieckmann-de Broglie function psi. But the inner sum is now over the second largest prime factor p. Now, at this stage, so when you do the same thing for the second largest prime factor being L mod k, you have to have the same condition, but the p will now be L mod k. So that's what is going to be inside. But you see, I'm proving here that the second largest prime factor is uniformly distributed mod k, but in the inner sum, in my own opinion, I'm choosing roughly 1 over phi of k of the total sum, but I have to actually prove that the actual contribution is 1 over phi of k. So how do you do that with a sum? So here is the trick. You take the sum and you compare it with an integral from using the prime number theorem, and you study the resulting error. The resulting error turns out to be quite small, so you conclude that the term which has got the integral, which is written in 71 here, is actually x that you had originally, plus the error terms that come from taking the difference between the sum and the integral. The moment you have that, you have a handle on the proof. Why? Because now when you go to the same sum with L mod k, which is what I call here, what you now do is you compare it once again with the integral, but now the integral is using the prime number theorem for arithmetic progressions. Now in an integral, it makes no sense to say you take 1 over phi of k of the points on the interval from 0 to 10. Of course, in measured theory, yes, measure 1, 10 over phi of k. But here, it means you put the constant phi of k outside of the integral. Therefore, when you convert this into an integral, automatically the 1 over phi of k comes outside. And therefore, you are able to show that the original sum is x over phi of k plus this, and therefore you prove that the sequence of second largest prime factors is uniformly distributed modulo k. So it comes really out of this trick. This trick was there in my 77 paper, but to use it here for the second largest required more difficult calculations. And it's the same trick that this younger group is using when they are using the Cherepanov density theorem. Okay, so once you have that, I go through the same thing that I had before to show that this sum is little o of x. Then I show that the sum with the largest prime factor with the, hold on. So I show using Axel's theorem. And finally, when I use the uniform distribution result, that's the x over phi of k. You see there, 1 over phi of k comes out. This sum becomes small, so you end up showing the smallness of this expression. Axel's theorem method works in exactly the same way, but I want to just show you a miracle takes place when you go and do the integral part. When you do the integral part, what happens is you do the integral part with this difference. That's what is there in the duality. But what I want is mu n omega n of f of p of n. So I got to bring this minus 1 to the other side and make it a plus 1. But when I do that, that also is an x over phi of k coming to the other side. So these two things cancel, and you end up showing that this sum with the omega is actually little o of x. So the entire procedure goes through, and we get our main result. So the miracle is really the cancellation. So now let me point out something else. So there are 2 or 3 things that come out of this. I started by showing this result here. In a similar vein, I can now show that if I look at omega n like this, I get little o of x. If I use fractional part, I get little o of x. Hold on. When I get integral part, I get this. And now you will say, this is the same theme. What's the big deal? What is the difference? The difference is right here. When I do this, I end up getting a function of the second largest prime factor. But if I only look at the minus 1, I get a function of the largest prime factor. So I end up getting this difference. So what this means is, when my f is the characteristic function of primes in an arithmetic progression, the average is still the same, 1 over phi of k. The two things cancel. So now my theorem will be reformulated as follows. If a function, bounded function on the primes has asymptotics, which is kappa, And if the average on the second largest is kappa, the same kappa, then this sum becomes 0. Now, why do I emphasize this? I have a problem in my paper. Does there exist a bounded function on the primes such as maybe it has one average on the largest prime factor and another average on the second largest prime factor? I have not been able to find such an example. I conjecture that such a function does not exist, but I don't have a proof that such a function does not exist. But for my purposes, for my function, which is the characteristic function on primes and arithmetic progression, all thing is over. So in conclusion, let me say that my student Seon Sangupta has taken these same results and now applied it in the context of algebraic number theory and obtained similar slicing results from mu and omega n using the Shabatarov density theorem. And the general result that I have, I'm working with another PhD student of mine, Yazan Alamoudi. So this has been done in the context of Galois extensions and actually more general extensions by Ken Ono and his group. I give you a whole bunch of references for you besides my paper, and these are all papers of the Ono group, but we rely heavily on the Lagarius Odlyzko strong form of the Shabatarov density theorem. But I think this paper will have as much implication and excitement as my 1977 paper, except that for 40 years nobody looked at these higher order dualities, and I thought I should present this at this conference. Thank you.
So thank you very much. You succeeded to show your 72 pages in half an hour, what you did in 1 hour before. And also now we know much more about the second prime divisor of the numbers. And I expect next time you will tell us about the third prime divisor. Okay.
Being worked out with Sengupta again. Okay.
So are there further questions? Yes, please.
Can you say a few words about what is known for non-Galois extensions like this? You said Ono was doing something.
So whatever is known is for Galois extensions. I don't think there is any paper that we have seen so far for non-Galois extensions, but now let me make one point here. Madeline Locus Darcy, the PhD student of, former PhD student of Ken Ono, first did it for Galois extensions of Q. And of course used the Shabatarov density theorem in that case. Noting that when the extension is a cyclotomic extension, that is abelian, and therefore the conjugacy classes all have size 1, so this ratio is always 1 over phi of k. That corresponds to my case, which is the prime number theorem for arithmetic progressions. Then subsequently, Sweeting and Wu considered any general Galois extension of an arithmetic, of a number field, not necessarily of Q. But when they did that, they had to formulate the Mobius function and my duality identities in terms of prime ideals, and therefore and their norms, and then the smallest and largest and so on. So they had to establish a bunch of results before they could do that in that setting. But for the regular Galois extension over Q, the initial results that were obtained did not require such a complicated thing. Okay, so it went through routinely. So is yours a good question, but I don't know of any results. But I think this opens up several possible avenues of exploration.
Any further question? No? So let us thank the speaker again.
Thank you. Thank you very much. Thanks.
So we start in 5 minutes.
No, that's it.
जा सकता हूँ माइक बाथरूम जा रहा हूँ माइक्रोफोन के साथ ठीक है ना माइक ले जाओ
माइक
बाथरूम जा रहा हूँ ठीक है great
So let us go for the second talk of this session by Professor ICNTRT on modular representation theory using calculus. Please.
Thank you, Professor Waldschmidt. Thank you to Anuj and Anjuman and Shauli. I see some of them here for the invitation to speak here. It's lovely to be back here. My talk is more on the algebraic number theory side, so sorry for the phase shift, but there's some calculus in it, so hopefully that's a transition from analytic to the algebraic world. But you know, there's some finite fields there, and they showed up in Professor Adhikari's talk too. So this talk may look a little isolated, but it's part of a larger program I have to use the p-adic Langlands correspondences to compute some information about Galois representations. So I won't be able to say much about that in this 30 minutes, but you can treat this talk just as sort of independent facts from representation theory of GL2FQ, GL2 of finite field. But the vector spaces on which this group is acting are going to be vector spaces defined over finite fields. So it's what's called modular representation theory. So the characteristic of the field over which the representations are defined is the same as somehow that characteristic divides the order of the group also. It's a little unusual. Okay, so you start. So that VR. We saw some symmetric powers already earlier today in Kanenika's lectures, but here are some symmetric power representations of this matrix group, but we have a model for it in terms of polynomials. So let's look at all polynomials. This is sort of going to be high school mathematics. Homogeneous polynomials of degree R in two variables defined over a finite field. Sometimes we'll just take the field P, Fp, sometimes I'll take Fq, sometimes I'll take Fp bar, the algebraic closure. Let's be simple and start with Fp here. And the group GL2Fp, let's slow things down a bit and start with the finite field with P elements rather than Q elements. This acts on such polynomials. If you have a matrix, and it just moves the polynomial around by moving the variables around. Okay, so that's a natural vector space. You're just making the group act by changing the variable, substituting, and then get a new polynomial. So this is a nice modular representation of GL2FP, and it's a classical theorem. I was trying to look up the exact reference. I don't know if this is exactly correct, but let's say Brouwer-Nesbitt from 1941, there's an analysis paper, which says that this representation is irreducible only for small values of r, more precisely, if r is between 0 and p minus 1. In fact, this is almost a complete list of the irreducible representations, up to twists by the determinant powers. So up to twists by determinant powers, this is actually a complete list of irreducible representations. So this is one fact. And so what happens, for example, if you take r to be p, you take polynomials of degree p, indeed, if you look at Vp, so this is polynomials of degree p, then if you're teaching calculus or algebra in the US, something called the freshman's dream. So x plus y whole to the power of p, many people expand that as x to the p plus y to the p, but that's actually true in characteristic p, right? So if you look at this subspace spanned by these two monomials, right, and you put ax plus cy to the p here, all the middle terms will die and that space will be stable. So that shows you that polynomials of degree p have this subspace, so this is not an irreducible representation. Okay, so that's why that fails. And a bit more interestingly, if you look at the r for r bigger than p plus 1, then there's a famous polynomial called the Dixon polynomial, which is the following. It's called theta, x to the py minus xy to the p. P is a prime, of course. I have to say that here. If you look at this polynomial and look at all polynomials which are divisible by this polynomial, so space generated by theta means theta times q, so p is theta times q, then this is also stable because this particular polynomial, again by the freshman's dream and things, this polynomial is stable by the action of GL2FP. The determinant comes out as a constant, it's a small computation, and you wind up just with the theta polynomial times some scalar. You make a GL2FP act on it. So again, this is not 0, and this space is therefore reducible. So it's reducible even for r bigger than p plus 1. Okay, so good. So what you could do then is look at the following quotient. So maybe proposition. This goes back to University of Chicago thesis due to Glover, 78. You can look at the remainders, space of remainders. Let's call this space, sorry, this is VR1. If there are typos, please tell me. So polynomials which are once divisible by theta, that's a subspace of all the polynomials. Look at this quotient, VR mod VR1, and he proved using literally high school methods, define, there's some, basically some x's and y's here and some x's and y's here, the degrees of polynomial are here the degree is s. He mapped particular monomials to particular monomials, and he came up with a GL2FP equivariant map, an isomorphism, which respects the GL2FP action on both sides. He proved this if R is congruent to S mod P minus 1. So that looks somewhat interesting. It's a sort of a periodicity result of some kind. R and S are getting larger and larger, but as long as they're in the same congruence class mod P minus 1, then these quotients are isomorphic. So there's this sort of elementary proof of Glover, but nowadays, there's an observation due to Sandra Rosenstein that you could sort of prove this in just sort of one line, so to speak. if you observe that this space is actually an induced space. So if you work in group theory, you know what induced spaces are, but maybe I'll define it. So let me just let you stare at the notation first. So this is the induction from the Borel subgroup. So this is the space of upper triangular matrices in GL2FP. A, B, D are infinite field, AD non-zero. So this is a subgroup of that, and you're inducing a particular character, the D to the R character, takes this matrix A, B, 0, D to D to the R. That's why it's called the D to the R character. You take the lower right entry and raise it to the Rth power. Okay, and what is the definition of such an induced space? Maybe I'll just define it here. So in general, if you have induction from H to G of, so if V is a representation for H, this space has a model. You can just think of it as functions from G to V, which satisfies some invariance property. So it's all functions, set-theoretic functions from G to V, such that f of Hg is H dot f of G, and this is the V is a representation for H, so this is a group action. It's a vector in the vector space. Okay, so that's just the definition, and the group acts on the right by right translation. That doesn't mess with the property we have here on the left. So that space is stable under right translation. That's the induced representation. So given a representation of H, you immediately get a representation of G by induction. And if you look at this particular induced representation, it turns out to be isomorphic. So this is not so surprising here because the index of this is p plus 1. And this is the space of all remainders dividing by a polynomial of degree p plus 1. So this dimension is also p plus 1. It's a finite dimensional space. Both these things have the same dimension. That's easy to see. Why does this imply that? Well, this character is periodic mod p minus 1. If you take a non-zero element of a finite field and raise it to the R power, if R is going to S mod p minus 1, R is going to S mod p minus 1, then d to the R is equal to the d to the S, right? So this you can replace d to the R by d to the S and then reverse this isomorphism with S, and you might immediately get the previous result. So that's nice, and maybe I should say what this map is. So given a polynomial, I don't have much space here, but let me write it here anyway, so I don't have to erase what's below. Given a polynomial p here, you want to define a function, right? There's a space of functions. So which function do you sort of a nice, very nice function. You send a matrix ABCD in the group GL2FP to a vector. Now this is just a one-dimensional representation. So you send it to the lower, you evaluate the polynomial at the lower row of the matrix. Okay, so this is the element in FP. Polynomial is defined over FP. Just evaluating the polynomial at the lower row. You can check many of these little things hold, that it's invariant under H and things. Okay, so just evaluation of a polynomial at the lower row. Okay, so now we understand that Glauer's result can be recovered by just recognizing this space of remainder polynomials as an induced representation. Okay, any quick questions while I'm erasing? Okay, so this was about the history of the subject until I started looking at this with postdoc Rindam Jana at TIFR until recently, and now has moved to ICNTRT Bherampur. So here is some generalizations. We did send the proofs in yesterday, but maybe it'll appear next year. So what about spaces where the polynomial, where your polynomial is divisible by higher powers of theta? So let's define that space. VR m plus 1 to be the subspace of VR generated by theta m plus 1 at powers of theta. Can you do something a bit more, for example, for polynomials which are twice divisible by theta? Okay, so here is some facts. So when m is equal to 1, we prove that this space is isomorphic to another induced space. By the way, these representations are called principal series representations, some nomenclature. Character of the Borel induced up to G of the group called a principal series representation. So these are a bit more sophisticated than principal series. It's not really a one-dimensional representation you're inducing, a two-dimensional one. So okay, so what are you doing here? You're looking at V1. V1 is just linear polynomials. Polynomials in x and y, linear, ax plus cy or something. But you're restricting that representation to Borel and twisting that by this character, which is already defined over there. And then you're inducing that up, as in that definition, and you wind up getting this particular quotient. And it turns out that this is not always true. You have to assume that P does not divide R. R is the degree of the polynomials. Okay, so this looks like a slightly strange fact, but what is interesting is that this map is an explicit isomorphism. So given a polynomial, we have to give a function which to a matrix takes an element, a linear polynomial. So let's just say it has two coordinates. And what are the two coordinates? Turns out the coordinates are 1 over nabla, P, CD. So remember, in this case, it was just evaluation of the polynomial. It was just a one-dimensional thing. And now you have a two-dimensional thing. You have two coordinates. So in the second coordinate, you just evaluate the polynomial, as before. But in the first coordinate, and this is where some creativity came in, we differentiate the polynomial with respect to a nabla operator. There's some calculus happening in algebra, which is unusual. Divide by R, that's the condition that P does not divide R, and then evaluate at CD. So what is nabla? Nabla is A ddx plus B ddy, partial derivatives. Okay, so you can prove something like this. There's another result where what happens if P divides R? Well, then you have to massage the other side a little bit. You have to replace this representation by a split representation. So let me not get into that, and you have to modify that nabla operator a little bit. Let me continue generalizing this. Suppose that now m is even more general. We did m equals 0 over there, m equals 1 is over here. Let's look at VR mod VR m plus 1. So I did the m equals 1 case separately just to lessen the load on the amount of notation. But suppose that P doesn't divide the binomial coefficient R choose m, then this is isomorphic to, again, in induced space, dr minus m from the Borel to GL2FP. So this space you're inducing gets a little bigger depending on m. You twist by a character which also depends a little bit on m. And then you induce up. And the definition of this map is very similar to this one. There's many more coordinates, and there's some binomial coefficients that appear here. And that's where you use this fact that P doesn't divide R choose M. Okay, so but there are many more nabla operators, powers of nabla operators and things. Maybe I'll skip the exact definition. Okay, so a corollary of this is that you get a more general kind of periodicity for these quotients of symmetric power representations, these generalized remainder spaces. This is something that I was looking for with another ex-student, a postdoc at ISC Bangalore, Ravi Teja. And we managed to prove some things using some dual numbers, but this is a little sharper than this and more simple to prove. So corollary, whenever m is between 0 and p minus 1, and p doesn't divide two binomial coefficients, r choose m and s choose m, and r is corresponding to s mod p minus 1, then the spaces of remainders are isomorphic. Again, the proof is evident from here. This is independent of r. That's the key point. There's a Vm here. M is fixed. The only slight dependence on r is the power of the character, but if r is going to s mod p minus 1, this character is the same. D to the r minus m is equal to d to the s minus m. So you immediately get this. Okay, so the title of the talk was GL2FQ, not GL2FP. So let me state a further generalization of this. So now suppose you're working with a finite field with p to the f elements. F is any number bigger than or equal to 1. Then, so let me first tell you what the irreducible representations are essentially. So again, the same paper of Brower-Nesbitt says that you take tensor products Okay, so what is this? These are just spaces of polynomials, but now there are many variables. Each of these is, for example, this is an x naught and y naught, polynomials of degree r naught, an x naught, y naught. These are an x1, y1. These are an xf minus 1, yf minus 1. GL2f q acts, maybe I won't write it down, but GL2FQ doesn't act diagonally on the polynomials. What you do is there's the Frobenius map, right? FQ has a canonical Galois automorphism, x goes to x to the p, which takes FQ to FQ. So what you do is when you have a matrix, you first make Frobenius act on it. A, B, C, D goes to A to the p, B to the p, C to the p, D to the p, and then make it act on that factor. Do it Frobenius act twice, and on this factor, etc. F minus 1th power, and then you make it act on the variables on that factor. So you have this huge tensor product, and GL2FQ is acting on these tensor product in this way. Turns out that these are more or less exactly a complete list of the irreducible representations, up to twist by determinant again, they're all. And one can ask if there's a similar theorem for the remainders, and indeed there is. So up to this point, the theta polynomial was discovered by Dixon, etc., and it was very classical, but checked in the literature, there were no analogs of the theta polynomial in the literature for GL2FQ. So we had to invent something. And we came up with the following result. All these are part of the principal series section of that paper. So let the mi's be small, I is between 1 and f minus 1 each time, or maybe 0 and f minus 1. And the ri's are a bit large now. There the ri's are small. Here the ri's are big. This is just extra general culture. Just introduce this so that you see this notation. But back to the lecture, the theorem is that if you take this tensor product and mod out not by the powers of one particular theta polynomial, but a whole bunch of them, then you wind up getting an induced representation. This time you take the Borel of FQ, upper triangular matrices, GL2FQ, and it's very similar to the previous theorem. instead of Vm, you have a whole bunch of Vmi's. You tensor them all together. Borel is acting by Frobenius powers on each of these, and you twist with d to the r minus m. And here, p does not divide any of these binomial coefficients, none of these binomial coefficients. P doesn't divide r choose mi for any I. D to the r minus m is a shorthand for d to the summation ri minus mi p to the fi I e, p to the j, sorry, p to the I equals 0 to f minus 1. So d to some power, but you take all possible powers ri minus mi, but with appropriate powers of p and add them all together. Take that character. So this is all obvious notation. Similarly, you have the Borel for GL to FQ. Okay, and you immediately get, oh, so what are these polynomials? So here, theta I took a lot of sort of messing around with computations to come up with this, but turned out to be something quite simple. These polynomials are these polynomials. So it's a negative of the previous one, but the key point here is that the variables are sort of interlaced in this weird way. You have xi and then yi minus 1 to the p, etc. Okay, and then you get a periodicity results. Any such quotient will be isomorphic to any other such quotient with s's everywhere, as long as p doesn't divide all the RMIs and all the R choose SIs, just because this space on the right side is independent of R and S completely, except for in a very weak way. But if the R and S are the sum of Ri p to the I is congruent to S, which is the sum of the Si p to the I's, then this character will be the same, and you'll get that these two quotients will be periodic. For large R, the remainder spaces only depend on the congruent class of R mod Q. Q is p to the F, p to the F minus 1, Q minus 1. Okay, so this particular statement is expected to have some applications to compute. Whatever I do in my life, there has to be a modular form somewhere in the background. So I know this audience is in love with modular forms, and so am I. So if you take a Hilbert modular form and you have its Galois representation and you want to reduce it mod p and you want to study what the shape of the Galois representation is, you need to, when you transfer this by the Langlands correspondences to the other side, you need to understand such quotients. And knowing periodicity and things like that, knowing that these things are principal series, etc., is very useful. So let me just leave it at that. Am I over time already? No, what time do I? Oh, I have 5 minutes, great. Good, so I can talk a little bit about the Cuspal case. So this is so much for the principal series case. Let me say something now about Cuspal representations. So if you're a little bit familiar with these matrix groups, then you'll know that there are essentially two families, interesting families of representations. There's the principal series ones and the Cuspal ones. And they're kind of dual to each other in some sense. These have dimension p plus 1, those have dimension p minus 1. In the middle you have the Steinberg representation, this isolated thing. And of course you have the one-dimensional representations. So there's another side of the picture, the cuspidal side. Let me see if I can say that in a few minutes. So let me make a little remark here before I do that. Variant. Let me go back to the very first theorem, VR mod VR1. And let me multiply, tensor that with Vp minus 1, another space of polynomials. Then I would have to take the character induction d to the r. So if you remember, there's a Borel here, the Borel of Fp to GL to Fp, the very first result I stated. If you tensor both sides with Vp minus 1, it turns out you can move the Vp minus 1 inside to come up with a bigger space. And what you do is you put the split torus here. So this is just the diagonal matrices inside GL to Fp. So this is just a immediate corollary of that. I want to state this because the cuspidal things will be stated in this language. So let me get to the cuspidal case. So the reason I introduced this torus is there's another torus inside GL2FP, another abelian group, which is the non-split torus. You take a quadratic extension of FP, take its non-zero elements, and it sits in GL2FP, just like the complex numbers sit in 2 by 2 matrices of the reals. U plus V alpha goes to this matrix, U, V alpha squared, V, U, where alpha squared belongs to FP. Alpha does not belong to FP. You just take any element of the finite field, take a square root of some element. That will generate the quadratic extension of degree 2. And you look at this is these 2 by 2 matrices. This is a bijection with these elements. So that's another abelian group sitting inside GL2FP. And let me define omega 2 to be the character, which is the identity character. Okay, so really there should be a matrix here. This is a character of the group GL2FP, or of the torus, sorry, of the torus. So I'm just taking it to U plus V. This is more or less the identity character. So here is the cuspidal analog cuspidal theorem. Remember, on the right-hand side, we had principal series kinds of representation. On the left-hand side, we have quotients of symmetric power representations. We want to follow that kind of model. So what if we induce, let me write the answer first, induce from the non-split torus GL2FP of omega 2 to the R, right? This character. This is the non-split torus, that's these matrices. You induce that up to GL2FP. Well, it turns out that this is isomorphic to a quotient of a symmetric power representation. It's a quotient of D. So this is for 2 less than R less than P minus 1. Okay, so what's going on here? Let me be very quick. So here we have a larger symmetric power representation, polynomials in 2 variables, but of degree R plus P minus 1. D is not a particular polynomial. Now it's a differential operator. This idea goes back to Serre. It's x to the p ddx plus y to the p ddy. You can check that the dimension will be p minus 1 when you differentiate this way. And the codimension there will be p minus 1. And I'm tensoring artificially with vp minus 1 like I did over here. And it turns out to be an induced space, something like this. So again, this is given by a very particular map. I'll just write it in if I can. It's hard to write this, I think, in this much space. Handwriting is going to degenerate, but I'll try. Nabla alpha is okay, so just to give you a flavor of what this looked like, again, given a polynomial, I have to give you a function. And what function do I take? I take a matrix A, B, C, D. I differentiate it R minus 2 times with respect to a yet another differential operator, Nabla alpha, which has some A plus C alpha, B plus D alpha in front of it. And evaluate. So what's interesting here is now that was sort of differentiable calculus. You're in the dual world of the cuspidal representation. Some sort of integral calculus coming in. You're evaluating this differentiated polynomial at 2 points and subtracting the evaluation at these 2 points. Like when you evaluate a direct limit integral, what is it called, a direct integral? Something similar like this happens. And then there's some fudge factor here, the q's. The q's are not so important. So again, one can prove such theorems using explicit differential operators. I should say that this representation is a cuspidal representation, tensor Vp minus 1. Just like in the principal series, you can pull out a Vp minus 1 and you get the usual principal series. Now you get a cuspidal representation. This is a notation I haven't defined. It's almost by definition. And so you can cancel Vp minus 1 both sides of this isomorphism. And this theorem was actually proved before our theorem, so it's a stronger theorem. Our theorem follows from that theorem. But the proof is very technical. It uses crystalline cohomology. So I had asked Arindam to try and prove our theorem after tensing with Vp minus 1 just using calculus and no fancy crystalline cohomology. And so that is a corollary of that. And there's a GL2FQ version of that also, which I won't write down. So thank you.
Thank you very much. Any question?
Yes.
Yes, please.
So how far are these from getting a Jordan-Holder, understanding the Jordan-Holder series of these representations?
Yes. So actually the principal series for GL2FQ generically has 2 to the F Jordan-Holder factors. At the socle, there's one particular weight. At the co-socle, there's one particular weight, and then it's sort of a diamond. Looks like Pascal's triangle, but 2 Pascal's triangle. I mean, there's 1 weight and then 2 weights, 3. That's the socle filtration. So there are 2 to the F weights, and that's exactly where that was known. In fact, it's due to some Indian mathematicians, I think, students of Brahma Srinivasan, maybe from Chennai also. So those results are well known. But if you transfer those results using this theorem, you get the Jordan-Holder decomposition of this. And that's what's useful in our computations. I don't know if anyone's tried to write down. Yeah, of course, there's not much to do there. It's one-dimensional. So the Jordan-Holder factors are not so interesting there.
Thank you. Any further question? Okay, so let us thank the speaker again.
Oh, yes. We have to back off. Thank you very much, Michelle. Thank you.
In your abstract, you say it is expected that our results will give some computation.
Yes,
What is missing for?
So now we have to apply the whole machinery of the Langlands. There's just some
Yes. But,
computation for GL2FQ, but then you have to sort of, there's some characteristic 0 version of all these spaces, and some Banach spaces, and some lattice in it. You reduce it in mod P, you get these kinds of spaces. And so once you have a lattice in a Banach space, you reduce it in mod P, you understand what it is. It's the same as on the Galois side, taking the Galois representation.
Excuse me, there is a small announcement. So we'll have a group photo in front of the main building of IMSC. So
Yes, well,
all of you, I
another
request
postdoc
all
is
of you
beginning
to
look
be
at
there.
it. So it
We'll
just
have a
started-
group
the
photo
project just
there.
started 2 months ago. So yeah.
After that, we'll have a tea here.
Thank you.
And after that, felicitation will be here.